Pyridine. Pyridine is an aromatic compound with a nitrogen in place of one of the carbons in a benzene ring. Here is the structure for benzene ring, and you can see if you replace one of the carbons in here with the nitrogen, then it's going to give pyridine. Okay, one thing to know about pyridine is nitrogen has a lone pair of electrons, and this lone pair of electrons is actually going to be perpendicular to the p orbital, which means it's not going to be a part of the pi electron cloud, which means it's not going to take part in the resonance. Okay, so let's answer this question. Why pyridinium ion is a stronger acid than ammonium ion? So here we have two structures. The first one is the pyridinium ion, where you can see that the hydrogen is attached to the pyridine. And the next one is the saturated amine of the pyridine. So which one is going to be more acidic? So in general, if you look into the acidity, one of the factors that would affect the acidity, it would be the electronegativity. The more the electronegative, the more if the hydrogen that is connected to an atom is going to be more electronegative, then that hydrogen can be lost very easily. So let's compare the acidity of these two nitrogens. So this nitrogen right here is an sp2 nitrogen. As you can see that there is a double bond right there. But this nitrogen doesn't have, is actually an sp3 nitrogen because you do not have any double bonds, right? So because of which an sp2 nitrogen is going to be more electronegative, and therefore the hydrogen that's connected to that sp2 nitrogen is more acidic. Okay, and therefore pyridinium ion is going to be more acidic, which has a pK value of 5.16 compared to that of pyridinium ion with a pK value of 11.12. Now let's talk a little bit about the dipole moment. Where is the how much is the dipole moment value, and in which direction it is in? So we know that nitrogen is electron withdrawing, and therefore the negative end of the dipole moment should be pointing towards nitrogen. So the positive end is in this direction. So reactions of pyridine. What are the reactions of pyridine? Pyridine undergoes reactions characteristics of tertiary amines. So the very first reaction that you can think of is it can undergo SN2 reaction with an alkyl halide. So let's write this equation. So when it undergoes an SN2 reaction, it's going to get alkylated at the nitrogen. Okay. So here we have our lone pairs of electrons on nitrogen, and that's going to go attack the electrophilic carbon, thrust these electrons onto iodine, and it's going to alkylate the nitrogen. So this compound right here is N-methyl pyridinium iodide, because the alkyl group is attached to the nitrogen. So it's N-methyl pyridinium iodide. Okay, now what are other reactions that pyridine can undergo? Remember, pyridine is aromatic. You still have those 3 electrons in the ring, and also it's cyclic, and all the atoms are in pyridine are planar, and therefore it is aromatic, right? And when we look into the resonance contributors, there are actually 5 resonance contributors. So here are the 5 resonance contributors, and you can see that just as we have 2 resonance contributors for benzene, we have 2 uncharged resonance contributors for pyridine. And then we also have 3 other resonance contributors which are actually charged, and that comes because of the electronegative ability of electron withdrawing ability of nitrogen. Okay, so because pyridine is aromatic heterocyclic compound, it can undergo electrophilic aromatic substitution reaction. Now, what's the mechanism? It's going to follow exactly the same mechanism as that of benzene, but one thing that we have to note down here is pyridine can undergo electrophilic aromatic substitution reaction only at 3rd position. Okay, so What is the mechanism behind the electrophilic aromatic substitution? It occurs in two steps. The first step is going to be the electrons from the double bond is going to go and attack the electrophile, which is a slow step. And then it's going to form the carbocation, and the base comes and obstructs this hydrogen, thrusts these electrons into the ring back in to give the substituted pyridine. Okay, now where does the substituent get added on to pyridine when it undergoes electrophilic aromatic substitution reaction? So normally it undergoes the substituent will go on to the third position. And now why third position? So in the third position, it's going to form equally stable resonance contributors. So these are the three equally stable resonance contributors. But in the second or the fourth position, you have one resonance contributor, which is going to be one intermediate, which is going to be less stable than the rest of the two intermediates. And the reason behind it is the nitrogen in here has an incomplete octet, and also remember it's an electron withdrawing atom, and putting a positive sign on electronegative atom is not going to be feasible. Okay. Now, pyridine. What about the reactivity of pyridine? Is it more reactive than benzene or less reactive than benzene? Remember, pyridine has a nitrogen in it, and because of which the intermediate that's obtained from the electrophilic aromatic substitution of pyridine is going to be less stable than that of benzene. Okay. And therefore pyridine is going to be less reactive than benzene in an electrophilic aromatic substitution reaction. In fact, it is even less reactive compared to the nitrobenzene. Okay, so, and if you're going to put electron withdrawing groups on pyridine, it's still going to decrease the reactivity of pyridine. Okay, pyridine undergoes electrophilic aromatic substitution reaction only under vigorous condition, and even if it does undergo, then the yields are very, very low. Okay, so this can be seen from the harsh reaction conditions that needs to be adopted for the electrophilic aromatic substitution reaction. So here we have bromination and sulfonation, and this is nitration. So the standard reaction for bromination is you just use the catalyst without heating up, but here you're going to heat it close to 300 degrees Celsius, which is definitely a harsh condition, and even with that you only get 30% of the product. And same thing happens with sulfonation. So you heat it close to 230 degrees Celsius and you get 71% of the product. And with nitration, there is only 22% of the product by heating it to 300 degrees Celsius. Now, what about Friedel-Crafts reaction? Does pyridine undergo Friedel-Crafts reaction? The answer is no, because when we look into the reactivity of benzene and substituted benzene, we know that when you have a nitro group present on a benzene, which is a meta director, it's not going to go the Friedel-Crafts reaction doesn't even occur at all. So with pyridine, which is less reactive than nitrobenzene, it's not going to undergo Friedel-Crafts reaction. Okay, so the answer is no.